Then I'll share my screen. Okay, so I hope my screen is visible. And for today, I want us to focus on doing the analysis. Just a quick recap on the analysis. And then after we've done our analysis, now we're going to start doing the design. Today is on Tuesday, on Thursday. So we're going to start doing our design on Thursday. We are going to start with the slabs, and then we are going to slowly progress to the other members. So basically, at this point, we've all understood what we have done. We started with the architectural floor plan. And then from the architectural floor plan, we were able to decide where we want most of our structural members to be, right? So we got to choose where we want our columns to be, where we want our beams to be, uh, the types of slabs we want, their depth. We got to make preliminary sizes, and then you also got to model the other members, such as the staircase and the ramp, right? Then after we model them, we got to load them and create the combinations. So at this point of the design workflow, what we want to do is to understand how our structure is going to behave when it is exposed to these loads in real life. So we want to simulate that. So what do we expect when, say, loads are acting on certain members? So we expect to have internal forces, we expect to have movements, and from those movements, but from the results that we get from those, say, the results we get from the analysis are going to guide us on what we do in the design. So in the analysis bit, what we want to do is to determine how our members are going to behave when they are exposed to the loads. Okay. And then in the design aspect, now we are going to be designing for the results we get from the analysis. So basically in design, what you do is for a given, say, for given moments, you are going to use the Eurocodes to determine an appropriate area of steel required. And then now from that area of steel required, when you combine now the steel and the concrete, you get a stable structure, something that can be built. Some of the members are not going to pass the design, okay, due to the nature of the forces or the magnitude of the forces they are exposed to. And when that happens, what you do is you have to resize them, or sometimes you may even have to remodel some bits so that you can probably orient them better or just optimize them if you need to. Okay, so that's the stage you are getting into. We are done with the modeling bit, so we are going to go into analysis first. So to do your analysis in robots, what you're going to do is just go to the calculation options at the top. I hope you can see this. I am going to go to the analysis at the top. We have the analysis tab here. You're going to click on analysis, and then you're going to click on analysis types. Okay. And then under analysis, we have a couple, we have types, we have different types in analysis. So how the software does this is it is going to analyze each case individually. So it's going to analyze the structure under self weights, under the wall loads, under the partitions, under each type of load you entered. And then it is going to do the analysis for both, for the combinations you did. So be it the ULS codes with the wins or the SLS. And then the results from this are what you're going to use in the design phase. So for example, say when it comes to sizing the column members and getting the areas or the number of steel bar required, for that one, usually use the ULS combinations. But say when it comes to determining the size of the footings, especially the area, we usually use the uh, okay. Am I audible? Am I audible? Someone please confirm that they can get me quite
Yes,
clearly.
you are audible, but maybe you should check your volume also.
Mm, okay. So let's go again. I hope I'll be clearer. I hope I'll be clear up. So, uh, as I was saying, so when we want to do our analysis, the software is going to be analyzing each case individually. So, be it the self weight, the main, all the say all the loads you entered, it's going to analyze them individually, and then it is going to analyze the ULS combinations as well as the SLS combinations or any other combinations that you may have. All right. So now from these analysis, what you are going to get are the results. And then we use the different type of results for different things. Okay. So the main results that we would be interested in are results from our ULS combinations and our SLS combinations. So for our ULS combinations, we are going to get the critical cases, that is the combination that gives us the worst case scenarios or the case that would give us the most loads. Okay. And then we are going to design against that. And then for the SLS combinations, we usually use it to size the footings. It is majorly used for sizing the footings. So getting the area of your footing so that you can compare it to the bearing capacity of a soil. That's where the SLS combination comes into play, and also for checking for the serviceability limit sets, such as for the deflections, etc. So we use the SLS there. All right, so I want us to run the calculation. And the first thing that you're going to do is to set the analysis types. So we're going to start with selecting the combinations. Before I do that, I'd like to repeat how we got here. So to get here, this is what we did. We went to analysis, and then we went to analysis types. Okay. And then I want us to set different analysis types for the various cases. So we have the linear type of analysis and the nonlinear type of analysis. So the nonlinear type of analysis is usually used to account for secondary effects, especially when you have lateral loads. So to account for those secondary effects, so the secondary movements that would arise from from the lateral loads or from other types of loads that would act on a structure, we use the nonlinear combination. So to do that, we change the type of load. You go to the case list, then you click on these three dots here, and then you select combination over here. So you're going to select the first combination, press shift, and select the last one. Okay. So you select this. You can press control and select them one by one, or you can select the first one, press shift, and with shift, say keyed in, click on SLS combination, and then click on these two arrows to select them. Then once you do that, click on close. And then once the case list appears here, click on change analysis types. So you're going to change that to P delta or the nonlinear combination. So I click on P delta, then click on OK. All right. So I'm going to have my combinations in the nonlinear combinations. And then for the individual say cases, I'm going to leave them as they are. I'm going to have them as linear. And then once you do that, that's all you need to do. You're going to click on calculations. So I'm going to let the software run the calculations. And then at this point, you may find a few errors. At this point, you may find a few errors. We are going to talk about them in a few. So let me click on no so that I can stop. So when the first error appears, that is when I have that error on what I got an error on incoherent mesh on edges. So when this error appears, it is not quite an error, it's just a warning to say. So some of them you can assume them. If there are errors, okay, sorry, this is an error. Don't assume the error, but if it's a warning, you could assume it. But now for the incoherent mesh, this is what you do. You just click on it and then look at the points where that error is. So to get rid of of these of this particular warning or error, what you just need to do is select the panels that have that error. So we have this panel here, then select it, then go to edit, not edit, go to options of finite mesh generation. So you select the particular panel, you go to options of finite mesh generation and delete the mesh for that panel only. Okay. Then select this one and delete the meshing for that particular panel only. And then once you do that, select the panel and mesh it. Use the local mesh generator. Okay, use the local mesh generator for it. Do it panel by panel so that you try avoiding getting that error. Okay, I think we had another one. I think it was right here. So I'll select this, delete the mesh there, then select this panel, delete the mesh, select this one, delete the mesh, select this and delete the mesh. Okay. Then once you do that, just mesh them locally. Mesh them locally. Okay, then you can just have a quick verification to see if you have no warning. It's still there. So let's see where that is. Okay, so still here. Let me redo this. Let me delete the mesh there. Here, so sometimes you may have to do this a couple of times so that you can get something that you can work with. Okay. And then let me just remesh it locally. Let's see what I have. Okay. First ensure it is Delaunay, then uncheck regular mesh, then mesh it. Okay, let's see. Okay, then I'll just verify to see if this area has been sorted. Ooh, I'm still getting it. So let me repeat that for these other panels. Just then mesh there. Let me first start is complex mesh generation. Ensure under methods, we said you check regular mesh. And then we can now do the local mesh generation. Okay, so let's see how the verification goes now. I think they will have reduced, if not completely. I should have less than I had last time. Not really. So let me proceed. Okay, let me do this. Verification. Let me select them, delete them first. Okay, then under analysis types, ensure the structure model Okay, set to 10 mm. That's okay. And then I think the main issue was these panels here. So I'll just remesh them slowly. Okay. Yeah. Where was the other one? Don't remember quite well. Let me select all these panels here. Okay. And then I'll just mesh them. Then I will run the, the check again. Let's see how it goes this time. Okay, so let me see where that is. Okay, so they have reduced. I only have this one here. So let me give it another try. So I'll just start with deleting it. Okay. Let me delete this mesh here. Then I will also delete this mesh here. Then I can look at how these panels have been modeled. So probably there's an issue with how they have been modeled. That's why it is persisting at that particular point. Let me see. Okay, pattern is correct. And then I can select all flows, refresh the mesh, and then rerun the calculation. I still have this error. It's quite a persistent one. So let's see where it is now. Let's see where it is. Uh, okay, well, okay, so we have this incoherent mesh on edges. It is going to be quite persistent on most of your models, especially if they are a bit complicated. But the thing with it is that it does not really have a big impact on the impact on the quality of results you get. So sometimes I think the software is just misbehaving because at this point you can see it is listed or it has been mentioned, but in the number of errors that I have and the number of warnings that I have, they're still zero. So at this point, I could assume it and proceed without having to correct it. And I would just tell you that this is something that you're going to encounter a lot. The incoherent mesh edges sometimes it does not go away completely. So when you are very sure that you have counter checked how you've modeled it. So when we checked this particular point, we saw that the panels have been modeled quite correctly. and that now they are not overlapping, and the column is also joining the walls. So the issue could be that it is trying to say to mesh to the node of the column, and that's why probably at this point we still have that error. But the thing with it is that it's not going to affect or negatively affect, not going to negatively affect the quality of the results you get or the design of your members. And you're going to see how that will come into play. So at this point, I'll just assume it. And if you give it a few tries and you're still getting the incoherent mesh on edges, I'd I just encourage you, if you've counter-checked and seen that you've modeled correctly, you could just assume it and then proceed. Provided here the number of errors that you're getting and the number of warnings that you're getting are zero, then you can proceed to let the analysis continue. The type of errors that I would recommend you have another look at your model or redo your work is if you're having the instability errors. Okay, so if you're having errors in instability type 1, instability type 2, instability type 3, those ones are those ones will need you to have or give more care to them so that you ensure that your structure is okay and it is safe to stand if I may use that. Okay, then the other error that you may get at this point is the isolated node, and probably members are not aligned to any story. So those are other two errors that you may assume because they do not impact the structural analysis. Okay, so even if, say, a beam has not been assigned the same story, the load takedown is going to follow the right paths. If you have isolated nodes, you could delete them. But if you are already doing your analysis, you could just let it run through. They're not going to affect the quality of your results. The results are the type of error, again, just to repeat, that you will have to give you'll have to give some consideration or a lot of consideration are the instability errors. And for the instability errors, they will only come they will only come up if you are they will only come up if your modeling was so wrong that the software cannot even do the analysis. Okay, so if you're having the instability errors, it is majorly arising from your modeling, especially the type 1 and the type 2. The type 3 could be associated, or sometimes it is associated with the meshing. So if you're having type 3, you can stop or pause the analysis from the bottom here. Try to delete your meshing, try to remesh properly. Try to look if there are areas where your panels are overlapping, or there are some small elements that you may have modeled that are not visible. Okay, so that one would also apply to separate structure. That would also apply to separate structure. So the type 3 and the separate structure error would be associated, or sometimes they're associated with the quality of your machine and to some extent your modeling. Okay, but for the incoherent mesh on edges, especially if it is just a small portion, you could assume it because this small portion over here is not going to affect the quality of your analysis or your design. Because, say, for panels, you would design, say, one panel and use those results to detail your other panel. So if it's a slab, you'd look at your most critical slab, design that panel, and then use those results for your detailing, or also for producing the design reports. So a small area should not cause you so much concern. Okay, the one that I would recommend you have a very good look at is the instability errors. Okay, so if you have those instability errors, type 1 and type 2 mostly, you may have to redo your modeling. Okay, and then if you have the separate structure, just redo your machine, and sometimes it will disappear. If it does not disappear, then it is informing you that your modeling could also be wrong. But again, you don't have to worry about those errors. If you get an error that you're not quite familiar with, just share a screenshot in the deep cubes or just tag or DM me or Abraham, and we are going to assist you with correcting them. Okay. So once you run your analysis, or I could pause there and take a few questions if there are any questions up to that point.
Hello, Captain.
Is there hello engineer?
Yeah. If we have like an errors now and the analysis is being running, are we
Yeah.
going to pause or we are going to stop so that we can correct the errors in the mesh?
It depends with the nature of the error. If it's the incoherent mesh and it's just a small portion, you could assume it and proceed with the analysis. If it's the instability errors, just stop the analysis completely and go and revise your model and ensure that you've modeled correctly. Is that okay?
Okay,
Hello?
thank you. Okay, thank you.
Derek? Okay, you're welcome. Derek, I can see your hand is raised.
Yes, engineer. Yes, engineer. Good evening to you, sir.
I'm well. How are you?
I am okay. So I got a certain message. You are telling me the number of nodes you have has exceeded the maximum for this version, and I could not proceed with the analysis.
That
Yeah.
your software has an issue.
Okay.
That's the software issue. It probably has not been activated correctly, so it is limiting you. It's like you're using a trial version. That's why it is limiting the number of nodes that you have.
Okay. So what
So
can I do, please?
if reach out to Captain West, uh, inform him that you have an issue with the software and he should assist you.
All right, please. Okay. Thank you, sir.
Okay, his contact is in the Telegram channel, the very first message. Just look at Wes. He has been tagged there. Leave him a message and he's going to assist.
All right, please.
Super. So now that you have done your analysis, the next logical step would now to visualize the results the results from your analysis. Okay. So from the results, we want to understand what are the magnitudes of the axial forces on the members, what are the bending moments on the members, how do they, the bending moment or the diagrams from the analysis we've done, how do they look? Are they in line with the things that we would expect theoretically? Okay. But before we go there, I would like to talk about something else in relation to the results before we get to talk about them. And what I want to talk about is these. Let me explain this. What I want to talk about this side. So what I want to talk about are these force components. We have talked about, how do you call this thing? We have talked about these. We have talked about
Local,
the yeah
you
the
have talked
axis
about
system.
local. Yes, the
Yes.
local axis.
Yes, thank you. I was looking for the word local axis. So we have talked about the global axis and the local axis. Okay, so this is where they come into play. When you are getting to understand or when you're getting to read the analysis results, this is where understanding the global axis and the local axis comes into play. So robot works in this way. You have the global axis and you have the local axis. So what you are seeing here in this 3D model, these are the global axis. So you have Z going in this direction, you have Y, and you have X. So these were at play when we were doing our loadings. Okay. But when it comes to reading the results reading the results from the analysis, we now need to talk about the local axis. Okay. So if you remember when we were modeling our slabs, we kept on insisting that you stay consistent with how you model your slabs. right? So we were advising you as you model your slabs to follow the same the same pattern. So if you start at the top, go clockwise from left to right, and then in this other direction for your slabs. The reason we were talking about that is because of the local axis. This is because for the slab, the first direction you model, the first line that you model, that is going to be your X. Okay, so this direction is going to be your X. And then the second direction is going to be your Y in the local axis. So this one would come into play in this part. So when you've done your analysis and you want to check the results for your slab, you want to have all your panels having the same local axis so that it is easier to understand. So that when you display your results, if you are displaying the moments along the X, you can see that they are going along the same direction. So the danger would be at this point here. So if you had, say, this panel here and you modeled it in such a manner, going downwards, so you probably have this as your first direction, and then this as your second direction. This would be your X, and then this would be your Y. So when you're displaying your results for X, you're going to have moments along this direction for this one. And then for this one, they are going to appear in this direction. And because they are going to be maps, they are not going to be cut like this. They may be a bit difficult to understand. So that's why we were insisting as you model the slabs, you model them in a very regular pattern. So you start from left to right, then you go downwards, or in a clockwise manner. So just to reiterate that, we've said the first direction for modeling your slab was your X-axis, and then going downwards was your Y-axis, and that will come into play when we get to read the results from the slab. Okay, so I'll just pause there for a minute. If you've understood the local axis system for the slabs and how they would impact our results, please type a 1. Let me know that we are together. If you don't want me to repeat, please type a 2. Okay. If you'd like me to repeat, please type a 2. If you are good, please type a 1. Let me know that we are together. Before I go to the beams and columns. Okay, so I think we are good. I'm now going to go to the beams and columns. So the beams and columns will have a different type of local axis. They are going to have a different type of local axis. And this is what is shown in this PDF here. So you are going to have 3 types of axis. You're going to have the X, the Z, and the Y. Okay, so for beams and columns, you're going to have 3 axes. You're going to have the Z, the X, and the Y. So let's explain that in a minute. So assume this is a beam cross-section. Okay, this is a beam cross-section. Let me draw a more pronounced one. So this is a beam cross-section. So you probably have 200 millimeters in this direction, and then you have the depth in this direction. Okay, and then to the side in red, I'm going to cut a longitudinal section of the beam, or something that you'd consider the column. So let's say this is a beam or a column. It has a length of, say, 3 meters or 5 meters. And then here you have the width and the depth. That would be something like 200 mm or 500 mm. Okay, so you're going to have different types of axes here. So I'm going to draw the axis in yellow so that you can see. So this axis, if you are to cut an axis along the length of the member, okay, if you are to cut an axis along the length of the member, this would be the X-axis. Okay, this would be the X-axis. All right. So if you are to cut a section, or if you to have an axis along the length of a member, say this is a column, this would be the X-axis. And if your beam would say look something like this, say this is the length of the beam. So in the beam, the x-axis would be in this direction. Okay, this would be our x-axis in the beam. I hope you are together up to that point. So in the beam, this would be our x. All right. Then now from there, we are going to go to the cross section here. So the cross section is just the face. I hope you can understand this. The cross section is just the face, and it's going to have two axes. Okay, so you're going to have this axis along the depth, and you're going to have this axis along the width. So this is the direction with the shorter dimension, and then this is the axis along the longer dimension. So this axis along the longer dimension is always going to be Z. This is going to be your major axis, and then this is going to be Z. Okay, this is going to be Z, Z. Okay, and then along the weaker axis or along the dimension that has the smaller dimension, this is going to be Y, Y. Okay, so this is important when it comes to understanding the results from the software. This is going to be important, and I just want to ensure that we are together up to this point. So if you are together, please type a 1. If you don't want me to repeat this, please type a 2. Where do I see the meeting? You can't see where you guys are. Okay, please type a 1 if you are together. Please type a 2 if you would want me to repeat. Okay, so let me take a screenshot as asked by Bill here. Okay, so I'll just repeat this for clarity. So we have three major axes for the beams and the columns. So x is along the length, and then x along the columns is also along the length. And then because it has 2 dimensions for the cross section, you have the shorter direction, which you'd consider the width, and the depth. So this direction, where you expect the member to have more stiffness, is going to be the Z, and then this Y is going to be the minor axis. Okay, so this is where it comes into play. So if you look at this diagram over here, you have the FZ. So if this is your beam, now where is my paint now? Okay, if this is your beam, you can see that it is deeper in this direction. So this being the major axis, so your shear is going to be in this direction. So when you are designing for beams, you're going to be majorly concentrating on the bending moments and the shear forces as well. Okay. Then when you are designing the column, you're going to be majorly looking at the axial loads, because these ones are the ones that are going to be causing compression and buckling, like for the column. So you're going to be interested in the point loads going in this direction. So when it comes to reading the results for the column, you're going to be majorly interested in forces in this direction. Okay, the Fx. And then for shear forces in beams, you're going to be interested in the force Fz. Okay, okay. Are we together up to there with regards to the axial loads and the shear force? So for the beam, this is the shear force, and then this is the axial load. Okay, so I hope you're together up to there. Then we have the torsional moments. So I want you to look at this. So which color can I use here? Let me use this. So if we have a force in this direction here along Z, if we have a force along Z, so this is the force, it is acting in this direction. Okay, this is a force that is acting in this direction. Okay, so to get the magnitude of the moment that this force would be creating on the section, you would multiply it with the distance along y. Okay, so by having this force, it's going to cause torsion along the y-axis and not along z because they're going in the same direction. I think just from basic physics or mathematics, to get moments, you are calculating the perpendicular distance from the point you are at and multiplying it by the force. Okay, so the perpendicular distance would be along y, so you multiply it with the magnitude and you're going to get the moment my. So if you look at these screenshots, you're going to see that my is the moment, is the torsional moment along the strong axis. Okay, and mz represents the moments that arise from having the force, say, incident on this face. So for these moments, you would multiply them with the distance along z. So this one would be the moments along the weaker axis. All right, so you don't have to worry much about that. I just need you to understand that so that when we go to view the results in the software, it becomes a bit easier to understand. Okay, I hope you are together up to that point. Are we together? Please type a 1 if you're together so that I can go back to the software. Super. So since you are together up to that point, so let's proceed to the software here. So now that after you've done your analysis, you're going to get your results as a finite element available. So at the top, you're going to get that the results are available. And then at the bottom, and let me move this. Where do I move? Okay, let me. Okay, then at the bottom, you're going to have this green circle over here. So this circle over here shows you that your results are available and you can use them for, say, for analysis or for not for analysis, for design and also for reading reading the members. Okay, so let's get to do that. So for you to visualize the results for your analysis, remember at this point what you are trying to understand is the impact of the loads on these preliminary sizes that we have. Okay, and then from the impact, when we get to the design, we are going to see if the preliminary sizes that we had recommended are viable for construction. So if they pass the design checks, then they are viable for construction and you can proceed to detail them and issue them for site. But if they are not viable, they are going to fail in the design phase. And then once they fail, you have to take the precautionary steps. So if it's increasing the cross-section sizes of the members, if it is increasing the depth of the slabs, then you do that. Okay, so let's visualize the results. So to read the results, you're going to go to results over here. And there are a couple of methods in which you can visualize the results. So there's diagram for members. Members are basically your columns and your beams. And then you have maps for members. Then you have maps. Maps are these maps here. These are maps for the panels. So your panels include the slabs and the walls. Okay. Then you have reactions, displacements, deflections, etc. And then we have the detailed analysis. So the ones we use majorly are the diagram for members so that you can be able to see, say, the axial loads on your column. How are they behaving? Are they increasing from top to bottom as you would expect? If you're looking at the shear forces on your beams, are you having the maximum shear forces near the supports? Okay, so those are some of the patterns that you'd want to see, so that if they are behaving in a manner that you expect, you take that as a cue that your analysis was correct and you can trust it for design. Then we have the maps. So for maps, you're going to be looking at the bending moments for the slabs. So when you look at the bending moments for your slabs and the deflections, you expect the the maximum bending moments will probably be near the midspans of the slabs. And then for your hogging moments, you'd expect them to appear near where you have your supports. Okay. And then for the displacements, this is just a table to enable you to see, say, the maximum displacement of your structure. And then from there, you can be able to see if it is viable for constructions or yeah. Okay, so let's get started. So we are going to start with diagram for members. And to do this, since you are only interested, say, you don't do this say one by one. So I'm going to start with selecting columns at story one, so that we can see the actual loads for columns at the foundation. Okay, this is something that you can easily do. So for example, if you are interested in selecting a column for design, so you can go to story one, select your columns, select all of them, and view them in a new window. Okay, so you select your columns. Let me exit. You just expand story one, right click to select all columns, click on edit in new window. And then once you get to edit in new window, don't unselect them, go directly to results and then diagram for members. So once you open diagram for members, you're going to get this pop-up. So you have the NTM. This is where you see the basic actions. So we mentioned them. You can see the FX. So for columns, the FX is the axial load. Then you can see the FY and the FZ. So you say the FZ is the shear force along the major axis. And then for FY is the shear force along the weaker axis. For columns, you don't expect a lot of shear force unless they are exposed to huge lateral loads. So for the columns, the shear force you would expect them to be quite small. And then you have the MX, the MY, and the MZ. So for the MX for the columns, this one is going to be quite important because this one represents the torsional moment. Okay, the MX represents the torsional moment. So let me show you how this is a torsional moment. So if this is your X axis along the length, if this column is being twisted along the X, so it's going to be, if you have a moment going along the X, it's like it is rotating the column. It's like it is, say, twisting the column. So that is our torsional moment. So for columns, that is something that you'd want to look at. So you're going to understand that MX is the torsional moment. And then MY is the moment along the stronger axis. And then MZ is the moment along the weaker axis. Okay, so now you understand that. And then these tabs that you can see here, the NTM is where you see the basic actions. Then you can see the deformations. This is if you want to see, say, the displacements for your entire structure. You can visualize them here. Okay. Then you have stresses. You have reactions. If you have your foundations, then you have your reinforcement and your parameters. So at this stage, what is important for us is that at the basic actions. We just want to understand how the loads that we have modeled, how are they affecting our basic elements. So to visualize them, you're going to check them one by one. So you can check the FX and then go to parameters and change how they are described. So you want to see labels. So click on labels. And then you would want the positive and negative values are differentiated. And then for the graphs, have them as field. So for you to visualize them, you select a force or an action that you want to see. And then you have the parameters. So you have the labels, and then in the positive and negative values, have them as differentiated and filled. And then you can click on apply. So once you click on apply, I'll go back to NTM. And at this point, it may look a bit more like, say, gibberish because it's quite busy and you cannot probably understand what you have here. So to make this a bit more presentable, you can increase the diagram scale here. So if it's 500, you could increase it to 1000, then click on normalize, and the results are going to be smaller. Okay, so you can increase this to 1000, and then the diagrams become, or the labels become smaller. Okay, and then additionally, you could just zoom in and click on normalize. And then once you zoom out, they become a bit smaller and easier to understand. Okay, so we have this. Again, we say the fx as the axial loads, and we expect the axial loads for our columns to increase as you go downwards. So at this point, what we did is we selected columns at the ground floor because this is where we expect to have our maximum axial loads, and we can see the axial loads here. So the results that you see here are case specific. So the results that you can see here, they look small because they are only due to the self weight. So I will select ULS combination with no wind and click on apply. And then I can zoom in to make these, click on normalize. So you zoom in and then click on normalize to make them a bit more presentable. And then you can see this here. So when you have this, you're going to have your worst case scenario in red. Okay, you're going to have your worst case scenario in red, and then the column with the least axial load is going to be in green. All right. So when you look at this, you just need to understand if this is something that say you expect to happen, which I think is what I would be expecting to be looking at this point. I would expect to have my maximum loads or my maximum axial loads for the columns at the, say, near the center of the structure, because they are holding more weight as compared to the columns on the outer edge. Okay, so for the columns, if you look at this properly, the columns are within or on the inside of the structure. They are going to be having relatively higher loads as compared to the columns on the edges. So you can see for these ones, most of them are below 500, except this one. And then for this one, for the ones within the column, especially this group here, most of them are even above 1500. So this is where this comes into play. So when you're designing your columns, you don't have to design all of them. You can choose which columns to design. Okay, so if you want to design columns here, you would prefer to go, say, for the interior columns, you would prefer to design the one with the worst case scenario, because if you get a combination in the sense that a cross section and an amount of rebar that can resist this amount of load, then it can definitely resist this load here and this load here. Okay, but also you would not want to use this cross section for this member here, because it would be a huge, say, over design. Okay, it would be a huge over design to have this column here have the same cross section as this one. You can see how large the difference in the forces that they are experiencing is. Okay. Okay, so that's how you can easily tell what you have. So I'll click on exit, and then I will select columns from the entire model. So to select columns from the entire model, all you have to do is go to your object inspector and then expand objects of a model, select all columns. Okay, and then if you want to view the results, you could just to have a better view, go to editing new window. Okay, go to editing new window, and with the members still selected, go to results, and then for the columns, because they are members, go to diagram for members. Okay, so I'm still interested in the axial loads for the columns before I go to the moments. So I'll click on axial load, FX, and then go to parameters, ensure the diagram description is by labels and positive and negative values, and then as differentiated, and this one as fields. Then click on apply. So if you have all of them, they become say more difficult to read because these diagrams are everywhere. So you can just zoom in and then click on normalize to make them a bit easier to read. So you can see what you have here. So when you look at these columns, so even if you selected a random one, change the change it to a ULS, change it to a ULS combination, normalize it. You could have these as, say, 5,000. And this is what you'd have. So if you look at all these columns, if you take, say, an example of this, you have the actual load increasing from the top going downwards. It is increasing. It is increasing cumulatively. Okay. But then when you get to this point here, where we have the basement wall, you're going to see that you have that you have that you have say that you have that the actual load is reducing. Okay, this might look like an error, but in real sense it's not, and I will explain why it's not an error. So when you get to this particular point here, some of this actual load is being transferred to the basement wall. Okay, so some of these are, because we model them center to center, they are being transferred to the basement wall. So that's why it appears like the actual load has reduced from this point to this point here. And that is only going to be noticeable on the outer columns where we have where we have the basement wall. So you're going to notice that once it gets here, it reduces, because at this point we have the basement walls, and at this point, these loads here are going to be distributed to the basement wall as well. So that one would help when you're designing your foundations, because your foundations are your strip foundation for the basement walls are also going to be used to carry this column. So they are going to be, they're going to be okay. You're going to ensure that that's okay. But if you look at the columns in the interior spans, if you look at the columns in the interior spans, you're going to notice that the loads increase as you go down. So you can see this one is 1511, at the bottom is 1678. So you can see that that is how they are behaving. So you can see that they are increasing as you'd expect. Then the other thing that you may want to look at the columns are the moments. So let me change this to MX and click on apply. And you can see the moments. Okay, you can see the moments along MX. You can change this to MY to see what you have. So for MX, you can see we have very little moments, and we have very little moments because these are torsional moments. Most of our columns are not under torsion, which is a good sign, because they are not loaded on beams. They are not experiencing any torsion. They do not have any force causing torsion, which I think is okay. And then we have the MY and the MZ. We have the MY and the MZ. So I think we could pause here to explain what is happening here. So if you remember, when we were designing, when we were modeling our beams, we were advising you to ensure that you try and approximate the loads that would be acting on your column. So say if this, let me delete this. So let me just delete this quickly. So when we are modeling columns, or when we are orienting columns during modeling, we were advising you to take a look at the beams. So you have your beams here. So let's say this is it's a slab panel. Okay, it has this long beam and these shorter beams. So what happens is if you have column here, you would want it oriented in such a manner that the longer section of the major axis is in the same direction as this beam, because you expect this beam to carry more load than this one here. So it's going to be exerting more bending on the column, and it would need a deeper section to resist that. There's no harm in modeling it this way. Okay, this is just a best practice. But sometimes you're not going to be in a position to always model this as it is, because sometimes you may find that there's an opening or there's some architectural functionality that is limiting you from modeling a column going in this direction. So these columns would be exposed to the same load, but you're going to find that this column here is going to experience, this column here is going to experience, it's going to require more reinforcement as compared to this one, even if they have the same, even if they have the same, even if they have the same cross section, concrete class and concrete class. So you're going to find that this one would require more reinforcement when compared to this one. So if you remember what we were talking about, we said My is the moment along the major axis, the torsional moment along the major axis, and then Mz is the moment along the weaker axis. So if you look at this structure here, you can easily tell. So if you look at this, for the moments along the weaker axis, you can see most of them are 0, 8, 8.92. You can see they're quite small. But if I change to My and click on apply, you can see they are significantly larger. So you could say that whoever was modeling this work, I think it was Caroline, whoever was modeling this work was optimizing the section set. They are going to have a more economical design. They are going to have a more economical design with it this way. Okay. So this is one way of viewing the results. It is not a really efficient way of visualizing the results because it is too jumbled up. It is difficult to understand what is going on behind these numbers. But the good thing is there are multiple ways of viewing these results. There are multiple ways of viewing these results. So for example, if you are interested in getting to understand how say a column section is behaving from top to bottom, I just need to select it. Let me orient my view properly. So if you are interested in understanding how this column, how the loads, how this column is behaving from top to bottom, then it would be easier to use this method. So there's another method that is called the detailed analysis. So you just select it and then you go to detailed analysis. It is going to open up as a given pop-up. And then this pop-up is going to look more or less the same than from what you had previously. And the beauty of this now is that it is one column only. Okay. So if you are interested in your axial loads, click on apply and you can see, let me go to parameters here, have them as we had before, labels and then differentiated and filled, and click on apply. So if I go now to NTM, this FX is my axial load. This is my column, only that it has been placed in such a manner just to understand it. So you can see that this is the bottommost part of your column, and then this is the topmost part of your column. So with this as it is, you can be able to see that your axial load is increasing continue cumulatively as you approach the bottom of your footing. Okay. And if you want to see the moments, say if you want to see the torsional moments, you can click on apply and see that it is experiencing very little torsional movement along its entire depth. And then you have the moments along the major axis, My. So you can see how it is behaving. So you can be able to see that. So if you are doing your design, you can be able to see where the moments are. Okay, and then if you want to see the moments along the weaker axis, you can be able to see this. Okay, and you can also do a comparison here easily. You can be able to see that for most of the sections that the moments along the major axis are more than the moments along the minor axis. All right, so I'll click on exit and we'll proceed from there. So this is just These are just ways of getting to understand how to read your results, to get to understand what is going on behind the analysis. So you can use them, you can mix them up. So this is how you would mix them up. So for example, if you have selected you've selected the columns along, you've selected the columns, the ground floor, okay? And then you went to view in new window, and you did what we did before. You went to results, diagram for members, and turned on the axial load. You have to go to parameters, change this to labels, differentiated, and field. So if you change this to applied, then go back to NTM, zoom in and normalize. So if you did this and identified the column that has the maximum, axial load, if you identified it, so I think it is this one. So once you identify it, you can just click on exit, and then you can select it along its entire depth or its entire length, so that you can have a better look at it. Remember, this is going to be a most critical column. And so when you're designing the columns, you're going to design for this column here. So you just go to results, then you go to, say, diagram, not diagram for members, sorry. You go to results, then you go to detailed analysis, just to view that particular column. And then you're going to see it here. And let me see what happened. Let me have my previous selection. So once you select that column, you go to results, and then you go to detailed analysis. You're going to have your column here. It's going to be shown here. So if you want to see your axial loads, click on apply. So you have your axial load. You can see they're increasing from top going to bottom. If you want to see the ULS combination, you just select ULS here. Remember, the results that you are seeing on screen are case specific. So once I select ULS no wind, these results that I'm seeing, they are for this case here. If you wanted to view another case, you just select it. See if it's balconies, you can see that they become smaller. But I'm interested in the ULS combination. This is what is going to be used for design. So just click on apply, and you can view them here. So the axial loads are increasing. Then the other thing you may want to do to see are the moments. So just check all of them, and you can see them. So you can see the color. So the orange here is the MX, that is the torsional moment. Then this color here, it coincides with MY. So these are the moments along the major axis. And then these are the moments along the weaker axis. So the detailed analysis, it enables you to have a better look or interact with your member more closely, or just understand it much better. Okay. So there's that. So I'll go back to my 3D view. I'll close everything, go back to my 3D view, and I want to show you something else that I would consider as a really cool. So at this point, we have not seen how the forces are, say, behaving in our beams. Okay, so to do that effectively, I'm going to do it in this particular view. And then we are going to scroll through grid by grid, getting to see how the beams are behaving under each section. It's like we are going to be cutting. Sections, say, along this point here. Then we see how these beams are behaving, how the forces are behaving for these beams. Okay, so to do that, go to view, and then in this view, go to results, diagram for members, and then for the beams, we are majorly interested in the shear force. So I'll start with the shear force, check shear force, then go to parameters, ensure labels is on, and then they are differentiated and they are filled. It's going to be easier to see click on apply and close. So at this point, it is quite jumbled up and you cannot understand this properly. So to see them view by view, you see where you have your 3D view, you can work with the YZ and XZ. So when you choose YZ, this is Y. So you are viewing beams along, say, this direction and Z only, not in 3D. So you are cutting a section along Y, and it's going to show the Z elevation. And then in XZ, you're cutting along the X. Okay, if you're together, please type a 1. Let me know that we are together. Please type a 1. I keep forgetting how to access the chat box here. Okay, so we are together up to that point. Someone else, I hope I'm not with Boniface only. Okay, so I'll repeat that for the case of Derek. So we've said we want to view the results for these beams, but in the way that they appear here, they are quite jumbled up and it's not easy to understand. So what I want to do is say, go to 3D and select XZ. Okay, and once I select XZ, this is what I have. So if I go to results here, diagram for members, zoom in and normalize. So if I go to this particular point, remember I'm only showing my axial loads. My shear force, Fz is the shear force for the beams, and then turn this to ULS combinations. Okay, so you can see the shear force for my beams. So what I have done is, instead of showing the 3D view, I have told the software to cut sections for me. Okay, so it's going to cut a section say along this part here. It's going to cut a section across the grids you have. So it can cut across here, across here, across here, across here, wherever you have a grid. And it's going to show you in this direction. So this is XZ, and then from your global axis system or global axis system, you can see Y is in this direction. So this is YZ and this is XZ. Derek, are we together with the XZ and YZ? Please type a 1. Okay, Abel, if my screen is slow, check your internet. It's probably lagging on your end. So we have that. Okay, so we have this here. So I'm going to go to view, and you have this. So when it comes to the shear forces, this is what you would expect, that you'd have majority of your shear force near the supports of the beams. Okay, so you expect your maximum shear force to be near the supports of your beams, and this is the reason. So when you're drawing your shear force diagrams, just to take you back to campus or your undergraduate studies, when you're drawing your shear force diagram, say this is a beam here. Okay, whichever side you choose to start from. So if you have your loads here, you're going to have your reaction right here. So at this particular point is where you're going to have the maximum force acting across the section of a beam. And then as you go in this direction, you have forces acting downwards. So as you go towards the center of the beam, depending on how the beam has been loaded, you're going to expect that these forces are going to be you're going to be subtracting from this reaction here. So as you go in this direction, you're going to be adding these forces and subtracting from here. So that's why it is going decreasing. And then once you get to the 0 point here, it is going to continue decreasing because these loads are increasing. And then at this particular point, you have another reaction that is going to be bringing it back to 0. And this is what you would expect to have for your shear force diagrams, especially for beams that are supported on both ends. Okay, so when you come here, this is what you expect. You can see your shear force is behaving in such a manner. Okay, you can see they are increasing in such a manner. And then at this point, you're just interested in seeing how it is behaving throughout the entire structure. So you're just going to click on this arrow sign, and it's going to move you through the different grids. Okay, so you can see it's going to change the axis here. So it's showing you which axis you are at. So you can see at this point you are at G. Then you're going to go to, if I click on this one, we go to grid 5. Then if I click here again, we go to grid 4, to axis 4. Then we have axis F. So at this point, we probably do not have any beams. That's why it appears that way. And then we go to axis 3. And then we go to axis 2. And then here is where we have the staircase. So we don't have any beams there. Then I will go to axis 1, and you can see what you have. Okay, so you can see that it is probably in line with what you have. If you have your axis 1, axis 2, you can be able to find each axis. If you have a beam of interest, you can be able to find that beam and get to see their results. And then for the beams along this direction, beams running in this direction, you would go to view and change it to YZ. Okay, you change it to YZ. And then once you go to YZ, you're going to have these beams here. You can also see the cladding. So you just click on these arrows. So if it is not increasing, you click on the lower one. Okay, so you can proceed, do this slowly, and you can be able to see how your beams are increasing. So if you get to a point where there are no column, there are no diagrams at that section, it probably means that for that particular grid, you do not have any for that particular grid, you do not have any members present. Okay, so you can be able to see this. And then if you want to make them smaller, just zoom in and click on normalize. Then if you want to see the bending moments, so the bending moments, let's see if I turn on MZ and click on apply. MY, sorry. So MY are the moments along the major axis. So you can see the MY where you expect your major moments to be near the midspans of the collar of the beams. So this is where you expect your maximum bending moments to be. And then near the supports, you expect some hogging moments. So at this point, you have some positive moments, and then at this point here, you have some other negative moments. Okay, so I'd say this is in line with how I would expect my structure to behave. And with this, now I can proceed to show you how to read the results from the panels. Okay, so I'll just I'll go back to 3D. So to go back to 3D, just come to here where you have YZ and click on 3D. And you'll go back to 3D. And then if you want to hide these numbers, if you want to hide these results, just go to results, go to the results table that you are in. You are in diagram for members, and then turn off here, click on apply and close. And you're going to see that. All right, so we have that there. Then the next one that you would want to do is to see the results from the slabs. We would want to see how our slabs are behaving. So we're going to visualize only one floor, because these floors are pretty much typical and they have the same loads. So I'm just going to expand, say, story 3, select all the floors here. So select all of them. then go to view them in new window so that I can isolate them. And then once I select them, I can click on top and just go to results. You don't have to press escape, but even if you press escape, you could just select them, go to results, and then go to maps. So at this point, we are interested in seeing the moments. So click on moments. You can see the moments along x-axis. So the moments along x-axis are the moments along this direction. Okay, the first direction you are modeling. I think when we were modeling, the structure was oriented in this manner. So this is our x-axis, and then this is our y-y. So this is why it was important for you to model using a very consistent, say, method. So if you chose this to be your first local axis for the slabs, I use them for all the panels so that it is easier for you to visualize the results. So if you're interested in seeing your moments, so just check the x-axis, then go to parameters. And sorry, you don't need to do parameters. Just check x-axis, ensure that with description is turned on, and then click on apply. And then you can see the maps have been drawn. Okay, you can see a map has been drawn, and you have a key on your right. So this map here is for ULS combination. If you wanted to have a different combination, you can be able to view it here. But since we are going to be designing using the ULS combination, I'll just check ULS combination and click on apply to view it. So if you look at your panels, where you have your negative moments, where your moments are, where you have your maximum hogging moments, not hogging, your maximum bending moments, they should typically be aligning with the mid spans of your slabs. So you can see where you have the mid spans of your slabs. These sections here is where we have our maximum moments. Okay, you can see where we have our maximum moments, and these moments are what we are going to be designing against once we get to the design phase. Okay, so wherever you have the mid spans of your slabs is typically where you have your maximum hogging moments. And then for this region here, where you have your cantilevered slab, you're going to notice that the moments look quite different. So the bending moment for these ones would be maximum near the edges, and then reduce as you go towards the support, depending on how it has been supported. Okay, and then for this is along x-axis, so this is along this direction. So I want you to see, once I click on y what happens. Look at the map, how this shape has been drawn. If I check on y and click on apply, you're going to notice that it now changes. Okay, so in the first one, this was the direction, and then in the second one, this was in the y, now this is the direction. So you can be able to see it is quite different, but the theory remains the same, where you expect your maximum moments are near the mid spans of the slabs. And then near the supports, where you have these orange, these positive moments are the 69, anything above 0 in the positive direction. These are your hogging moments. These are the positive moments near the supports. So when you come to detailing, these are the areas where you're going to be providing the top bars. Okay, so remember, we provide bottom bars majorly for tension near the mid spans. Okay, for tension, we usually use the bottom 1 bars, but for bending, we use the bottom 1 bars, and then for the bottom bars, and then for hogging, you're going to be reinforcing using the top bars. So at this point, you're going to be using the top bars. So this is why I like analyzing the entire slab. Okay, so when we get to designing the slab, when Engineer Abraham is going to be taking us through, you're going to notice something. He's not going to design for all the panels. You're going to design for the worst case scenario. So you're going to look at the panel, the largest panel, and design for that. So say if this is the largest panel we have, if we get a design that passes for this panel, then it is most likely going to pass for all the other panels. Okay, so you could use those results to detail for the entire slab. Okay, even those people who you say use Excel, if they are doing manually, you're not going to design for all panels one by one. You're going to select the largest panel, the critical panel, and design for it. Okay, but now modeling the entire floor plan gives you this advantage. It gives you this advantage here. It helps you decide where you are going to place your top one bars. Okay, so if you look at this, if you are not modeled the entire slab, it may be difficult to choose to place your top one bars up to this particular point here. But now since you have your result here, you're going to choose to have your top one bar along this entire point here. Okay. So there's that, it's going to play a role in that. So when we get to the detailing part, you're going to see that you're going to be having top one bars along these points here. And then typically for slabs, you do not have any top one bars near the midpoints because you can see they are literally not needed. There are no movements. There are no top movements at these particular sections. And then at these sections, bottom bars are rarely needed. Only that we need to from the Eurocode, when you're detailing your bars, they need to go to the support. Other than that, they are usually not needed at these particular sections. Okay, so that is one way of visualizing the results. Then the other way, the other result that you'd be interested in here are the soil reactions. So we're going to be modeling a mat later on. And when we model that mat, we are going to specify a bearing capacity. So when we do that, we are going to check the soil reactions here. At this point, it's going to be 0, because we have not assigned any supports or any planar support for this slab. But when we get to analyze our mat foundation, we are going to see that we are going to compare the maximum pressure that we are getting to the bearing capacity. So you're going to ensure that the maximum pressure we are getting is lower than the allowable bearing capacity that we have. And that is one of the most important results of looking at the maps, especially if you're doing your mat foundations. And then for detailing purposes, so that you can know where to place the various bars, the top bars and the bottom bars. Okay. I will go to something else. Just another way of looking at this. I'll just go to another way of looking at this. Let me have this as it was. Okay, I want you to look at my axis. You're pretty familiar with this. This is a long Y and this is a long X. Okay, global axis. So I will turn off this map so that you can see, or I don't need to turn it off. Okay, just let me take some water. So I want us to visualize another way of looking at the results. This one would be really important if you are designing something like a flat slab, where you want to see the effect of columns at given points of your slab. So this method is of visualizing the results is called the panel cuts. So you cut along a panel, you cut a strip, and then you can be able to see how movements are going to be behaving in that direction. So to access the panel cuts, you go to results and then you click on panel cuts. And then once you get to here, we are going to be using this second option over here, parallel to plane through a point. Okay, parallel to plane through a point, and then you have the option to pick either between YZ and XZ. So for YZ, you are cutting along Y, and for XZ, you are cutting along Z. So you just choose, let's start with YZ. So I'll have it as YZ, and then I will call this, let me call this cut 1. Okay, I know cut 1 is along this point. So I just want to see how moments are behaving along a strip throughout this entire slab. So I'll select this one, and then I will click at this point here and at this point here, and then I will click on apply. And then once I click on apply, I can just click on this particular point, and then you can see how they are behaving. So you can see the region where we had our, the region where we had our Hugin moments, our positive moments are the regions that we have. We have this, we have this, we have this particular, we have this particular positive moments here. Okay, and then this region we typically had, let me turn on the other method as well. It was results maps. Let me turn off description. So you can see at the region where we have the Hugin moments, you can see very clearly that these are positive moments because we've cut along the, the beam. So we have positive moments here, and then here where we have secondary beams, we have a bit of Hugin and then positive moments in this direction. So this is just a way of you getting to understand what is happening. This is just a way of you getting to understand what is happening. And then, for instance, if you wanted to cut along this direction, say you are interested in getting a view along the midspan of these two large slabs, how they look. So since we are cutting along X, you change this to XZ. Then you click on a point here. So you just need to click on a point, one of them. Then when you're adding a new one, since this one is a new one, you click on new. And then once you click on new, just click on one of the corners, or click on apply. And then once you do this, you can see how different this is because we have cut along, we have cut along the midspan. So you can be able to see, how those forces are behaving or how loads are behaving along that section there. Okay, so those are the major ways in which you look at analysis results from robots. Then the other one are the tables. So you could go to results, and then from results you go to forces. Okay, you go to results, then you go to forces. It's going to open this table for you. You can be able to see all the forces here, the Fx, the y, Fy, and Fz. This one is a bit difficult to use because it is pointing for all the nodes, and we have thousands of nodes. I think we have 33,000 nodes, so it's a bit difficult to use this. Okay, and it does not point you to the maximum, to where that particular node is. But you can see the maximum force is at 2083.36. This is the maximum axial load that we have for this combination here. Okay, if you look at this force here, it is going to coincide with the maximum force or the worst case force that we had for the nodes, for the most critical column. That support node. This is it here. This is its maximum axial load. This is where it is. So this one is not say that commonly used. The ones we used commonly are the diagram for members, maps, and panel cuts. And then we use the detailed analysis for individual members if you want to have a better understanding of them. And for let me show you something else here. So if I'm interested in seeing how these beams behave, so I can select these two beams, okay? I'll select these two beams, then go to results and detailed analysis. Okay, so I have to select one by one. Select a beam. Go to results, then detailed analysis. I don't know why that is happening, but there's another way. Just select a beam here. If this is of interest to you, select it. Then once you select it, go to object properties. Okay. You can see the forces of this beam by just selecting it. Then right click and go to object properties. And then once you are here, you can be able to see all the forces that are acting on this member here. So you can see its geometry. You can see its geometry, the material of concrete used. Then you can see the properties, the area sections, and the modulus of elasticity. Then you have the actions. So if you check the FX, you can be able to see it. So you can see the FX is maximum at the support. Then if you're interested in FY, you can visualize it there. Then FZ, you can see it is here and it's quite small. Then MX, you can visualize it. They are very small. MY, MZ, and so on. So you can see the bending moment, it's near its midspan. Then you have displacements. Majorly displacement, you are interested in displacement along Z. And you can see this entire beam only has a displacement of around -1 millimeters, which is fairly good. So that's how you visualize it. Okay. Then the other thing that I would want to show you is that you can visualize the displacements for your entire structure. So I'll go to view. Then to visualize the displacements, I will go to results, then diagram for members. Then you'll go to deformation. Just check nodal displacements, and then just click on start. So I will enter a scale. I will enter a scale of around 50 mm, and then I'll click on start. So give it a moment. It's going to if you look closely, you may not notice it, but my structure is kinda dancing. I don't know. I just try it on your end. You're going to notice that your structure is kinda dancing. Let me increase this to one is going to shout, but it's going to be, I think, more visible for you guys. Okay, so it may not look very clear at this particular point, but just try it on your end. Go to deformation, have a scale here, and you're going to see how your members are deflecting. So this one would be really nice if you had very long cantilevers and you want to see how they are deflecting, so that you can choose appropriate member sizes during the design phase. And that's how easy it is to run the analysis. So the only challenge I'm expecting, so probably most of you to face is the errors that would appear. So for the incoherent mesh, don't let it concern you. Just be concerned with the type, with the instability types and the separate structure. Okay. So that's all we had for today's session. If you have any questions, if you have any additions, this would be a good time. But with that, I will see you in the next class on Thursday. So thank you for attending and see you on Thursday.